The history of air pollution monitoring starts with the onset of the Industrial Revolution. This great economic boom, powered by the burning of abundant fossil fuels, brought with it unforeseen consequences to health and the environment. Following a series of devastating air pollution events in the 1940s and 50s, the U.S. Congress recognized that air pollution was now a national crisis and passed the Air Pollution Control Act. 3 years later, Oklahoma started its air quality monitoring program by installing a single lead monitor in Oklahoma City. When the first Clean Air Act passed in 1963, the Oklahoma Department of Health officially took over handling of all air pollution programs. After a series of amendments to the act, the monitoring process became more defined, but was not well established until 1970. The Clean Air Act amendments of 1970 set official air quality standards called the National Ambient Air Quality Standards, or NAAQS. These standards define the acceptable concentration limits for each pollutant of concern. By 1993, Oklahoma's air monitoring program had grown to address standards for carbon monoxide, sulfur dioxide, nitrogen dioxide, ozone, particulate matter, and lead. And it was in this year Oklahoma's state legislature created the Oklahoma Department of Environmental Quality, or DEQ. Since its inception, the Oklahoma DEQ has continued to adjust their network to monitor Oklahoma's air quality as accurately and efficiently as possible, operating approximately 35 sites across the state, with each site containing anywhere from 1 to 15 different instruments. So let's look at how some of these air monitors work. An instrument like this one is placed at a site and a line run outside to sample the outdoor air. A pump pulls the air from the outside into the instrument where it is then analyzed. A response from the instrument is then recorded and sent to the site data logger. The database and the software on the logger were specifically designed for use with ambient air monitoring systems. The software polls each instrument on the network at a regular interval. Once polled, that data is averaged over the course of 1 minute and stored. After 61-minute intervals, the software then averages an hourly value. It is this value that is often used for comparison purposes to that pollutant's NAAQS. All this data now exists on the site data logger, waiting to be transmitted to the DEQ Central Server for analysis. The Central Server is located at the DEQ Central Office in Oklahoma City. This server pulls each site's data logger every hour and is the permanent storage location for all of Oklahoma DEQ's ambient air monitoring data. At the office, the data is poured over by several people. The instrument operator looks over the data daily to verify the instrument is continuing to work properly. Quality assurance also reviews this data for anomalous readings and checks it with a series of strict data standards. Any data not meeting all standards are flagged or invalidated. Invalid data cannot be used to compare against that pollutant standard. After all quality assurance has been performed, the data is then submitted to a national air quality database for review by the EPA. All air monitoring data across the United States and Canada follow these same data protocols. Let's look closer at a couple pollutants. In Oklahoma, we have two primary pollutants of concern, ozone and PM2.5. Let's look at ozone first. You've likely heard of ozone in reference to the Earth's ozone layer. It's the same gas, but instead of being formed in the upper atmosphere where it protects us from harmful ultraviolet radiation, it is formed at the surface, where it contributes to smog and exacerbates health issues like asthma and causes issues with lung function. The best way to reduce concentrations of ozone is to reduce the chemicals used in its formation. Those chemicals mostly come from human activity, like driving, but also come from products like gasoline vapors, chemical solvents, and cleaning fluids. Here's a closer look at an ozone analyzer. As air enters the instrument, it first goes through a filter to remove any dirt or dust caught in the airstream. Then the airstream is split. One stream goes through a scrubber that removes all ozone. A second stream continues unimpeded. Each stream then goes through a long tube called a photometer. One side of the photometer has a light source that emits UV light. At the other end is a light detector. Ozone, by its nature, blocks this light, causing a lower signal at the detector. The difference between the two signals of the two air streams is how the instrument interprets the presence of ozone. After the measurement occurs, the pump continues to pull air through the rest of the instrument, then out the exhaust. Using this data alongside weather forecasting models, a DEQ team of meteorologists releases a daily air quality index, or AQI, for ozone, covering 5 regions: Oklahoma City, Tulsa, Lawton, Northwest Oklahoma, and McAllister. The AQI is a number and a color that simply describes the conditions of the air. If the AQI is forecasted to be unhealthy for sensitive groups or worse, the DEQ will notify local municipal governments who use their Ozone Alert programs to notify the affected regions that conditions are expected to reach unhealthy levels and precautions should be taken. Here's what an Ozone Alert looks like when issued by your local governments. You could see it mentioned on the local news, or you could receive notifications via email or text if you are signed up to do so. If you have not signed up for alerts, you can do so here. Now for particulate matter. Particulate matter, or PM, is another important pollutant monitored closely in Oklahoma. PM is all solid and liquid particles in the air, including, but not limited to, smoke, dust, pollen, and dozens of chemicals. PM is divided into categories based on its size. Particles that have a size of less than 10 microns are called PM10. Likewise, particles that have a size of 2.5 microns or less are called PM2.5. To put these sizes into perspective, if we blew up a grain of sand to be the size of this large children's ball, PM10 would be the size of a softball. PM2.5 would be approximately the size of a 6-sided die. Oklahoma monitors for both sizes, but it's PM2.5 that is of the most concern today. PM2.5 comes from fires, cars, trees, and any source of combustion. PM2.5 can contribute to visibility problems like haze, but the more severe effects are in the body. When these particulates are inhaled, they can get deep into your lungs, invading your bloodstream and causing lung and heart diseases. To better serve the people of Oklahoma, the DEQ employs 2 different types of monitors for particulate matter: filter-based and optical. For a filter-based instrument, the operator receives pre-weighed filters from a lab. They are then placed in a clean room where they are loaded into a sealed magazine and taken to the site. The filters are placed in the instrument, and the instrument is programmed to turn on for 24 hours for each filter. After the filters have collected their samples, the operator is required to receive the filters within a few days to prevent mass loss due to heat. They are stored in a cool, sterile environment until they are ready to be packaged on ice and sent back to the lab. The lab measures the filters for changes in weight and, in some instances, analyzes the filter for specific toxins or metals. This is instrumental for nationwide understanding of PM as a pollutant, but does not do much for Oklahomans in terms of real-time data. To provide for the necessity of real-time PM data, the DEQ has placed continuous PM monitors at many sites around the state. They utilize a real-time analysis technique called Broadband Spectroscopy, a fancy term for analysis using light. First, the air is pulled through a specially designed inlet called a PM10 head, which filters out particulates larger than PM10. The air is then dried and heated in a sampling tube between the inlet and the instrument, since water vapor can cause false readings on particle size. Then the air flows through an optical particle sensor. A light shines through a chamber and is scattered by the particulate matter that flows through the air. The intensity of the light scattered defines the size of the particle, which the instrument is able to read and display for the operator. Since this is a real-time technique, it is connected to the site's data logger. The same polling process described earlier is used to transfer this data from the instrument back to the DEQ office. When an instrument reads a number at a certain percentage of the PM standard, the central server sends an alert to a group of data analysts at the DEQ. After being alerted, the analysts critically review the data and decide if the public needs to be notified of an immediate concern. This notification is called an Air Quality Health Advisory. An advisory is an alert sent from the DEQ via email or text notifying the public when pollution levels are at an unhealthy level affecting sensitive groups or worse based on this real-time data. Here's what an advisory based on PM looks like. The areas colored in orange are the areas considered unhealthy for sensitive groups. Green and yellow areas are considered to be safe, and no precautions in those areas are necessary. Weather plays a large role in many aspects of air pollution. Cold weather means more particulates released from wood-burning fireplaces. Cars are left idle, increasing pollutant exhaust emissions. Thermal inversions are common in the winter, trapping pollution below and close to the ground. Hot, sunny weather allows for the reactions needed to create ground-level ozone. Heat waves dry out soil, allowing for wind-blown dust. Droughts dry out vegetation, which can lead to fires, adding more particulate matter and carbon monoxide to the atmosphere. On a global scale, you might have even heard of Saharan dust making its way from northern Africa all the way to Oklahoma. This happens as tropical waves with increased winds push fine sand into the atmosphere in the midsummer months. If it's thick enough by the time it reaches Oklahoma, it can cause air quality issues. You can often see the difference in particulate filters that are affected by Saharan dust, as they will have a yellowish-brown hue. Of course, weather can be very helpful as well. Frontal passages with strong winds can sweep ozone or particulate matter completely out of an area. Humid days can significantly cut ozone production, as the water in the air absorbs much of the UV energy required to produce it. Rain can wash PM and other pollutants out of the air in a process known as wet deposition. On rare occasions, there are air quality events for which the DEQ doesn't normally monitor, so existing methods are adapted to monitor those specific events. For example, during the Fukushima nuclear disaster of 2011, radiation entered the atmosphere and was dispersed around the globe via the jet stream. The National Mercury Deposition Network, of which the Oklahoma DEQ participates, instead of testing for mercury, began testing for radiation. No radiation was found in high enough levels to be of concern, but it does demonstrate the flexibility of Oklahoma's monitoring network in emergency situations. The DEQ works tirelessly to provide Oklahomans with the information and tools necessary to keep track of our air pollution, and to inform the average Oklahoma of how they can keep our air pollution levels low. Reduce the burning of wood and trash, carpool, use public transportation, bike or walk. If you do drive, make sure your car engine is tuned and your tires are inflated to the proper pressure. When it's time to replace appliances, choose energy-saving options and generally always try to conserve electricity. We hope you found this brief introduction to air quality monitoring useful and informative. For more information on this and other Oklahoma environmental issues, please visit the DEQ's website at www.deq.ok.gov.